Hey everyone, in this lecture we're going to study the types of binary trees. Now recall that in the previous lecture we saw some properties of binary trees and we also introduced the full binary tree type. Hence in this lecture we're going to continue to study the types of binary trees that we can have. First of all, a complete binary tree. In this type of tree, all levels are filled except the lowest level nodes of the binary tree, which are filled from the left. Here we can see an example of a complete binary tree. Notice that all levels of this binary tree are filled except the lowest level nodes, which are here in the last level, and they are filled from the left. Notice that in this left subtree we have these two leaves H and I that are filled. Also here in this leftmost part of the subtree, on the right of this left subtree we have J and K, and they're also filled. L and M, these two leaves are also filled. Notice that here we arrive to a subtree, particularly it is on the right, that is not fully filled. But what is important is that all the leaves at the left are filled, and this will always be the case. Even though we don't arrive to the last part that is not filled, we may have some nodes here in between that are not filled. What is important is that what we have on the left will be filled. Okay, let us now study some properties of complete binary trees. The first one is that the number of nodes that we will have at a depth d, it is going to be 2 raised to d. Notice that here this h, which is the height of the binary tree, will be greater than the depth. Now recall that we know that the height will be strictly greater than the depth because the height of a binary tree is the maximum level of a tree, and the depth, we can have any depth. So a node could be at a given depth. For instance, here the depth of node 5 is 2, but the height of this binary tree is 3. So what we are sure in this property is that if we are at a given depth d, that is strictly less than the height of the binary tree, then the total number of nodes at this depth is 2 raised to d. Another important property of a complete binary tree is that the height of a complete binary tree with n nodes is the floor of the logarithm base 2 of n, that is, of the number of nodes. Now, why is this property true? Let us think about this. Recall that the complete binary tree is defined as a binary tree where every level is completely filled except possibly the last, which is filled from left to right. So let us just define this step by step. First of all, in a binary tree, each node has at most 2 children. The tree grows by doubling the number of nodes at each new level. So starting at the root, at depth 0, the root is the only node, right? So the number of nodes at depth 0 is 2 raised to 0, which is 1. Notice how here the depth 0 is less than the height of this binary tree. Okay, so now, as we know, since this binary tree is complete, all levels from 0 up to h minus 1 are completely filled. The last level h may be partially filled. So the total number of nodes that we have is at least 1, right, plus 2, plus 4, plus 2 raised to h minus 1, which gives us 2 raised to h minus 1. Now these are the fully filled levels, and here we also need to add some nodes that we have on the last level, right? That is at the level h, at the level height of this binary tree. So since the value of n, the value of the number of nodes, belongs to this interval, we either have 2 raised to h or 2 raised to h minus 1, we can arrive to the conclusion that h, the height, is the floor of the logarithm base 2 of n. Another immediate property of complete binary trees is that all leaf nodes in a complete binary tree are present in the last level or the penultimate level. So as we know, in a complete binary tree, all levels except possibly the last are completely filled, and the last level is filled from left to right. So now let us think about the leaf nodes. First of all, we have internal nodes, nodes that are not leaves. These nodes must have at least one child, right? Since here, for instance, such as this one, A is an internal node, B also, E, C, F, G, and D. Moreover, in a complete binary tree, all levels up to the penultimate level are full. That means nodes on those levels definitely have children, so they are not leaves. Hence, the only possible levels where leaf nodes can appear are the last level, where some nodes may not have children, these are leaves. But also, at the penultimate level, some nodes may have only left children, and those children can be leaves on the last level, so their siblings without children may be leaf nodes on the penultimate level. In fact, the only nodes that can be leaves on the penultimate level are those whose children are missing on the last level, which happens only at the very end of a complete binary tree. So the rightmost part of the penultimate level. In this example, this doesn't happen, but in this other example, this indeed happens. Notice that here 6 is a leaf, okay, at the last level, but 3 is also a leaf, and it is at the penultimate level. So essentially, most leaves are on the last level and some on the penultimate level, although not occasionally. But what is important is that there will never be leaves above that, above the penultimate level. Okay, let us now jump to the following type of binary trees. This is the perfect binary tree. In a perfect binary tree, every internal node has exactly 2 children, and all leaf nodes are at the same level. Here we can see an example of a perfect binary tree. Why is this binary tree a perfect binary tree? Well, because if we examine it, we can see how all of the internal nodes, they have exactly 2 children, right? And if we look at the leaves, we can see how all of the leaves are at the same level. There is no missing leaf here, right? So all of them are in the same level. Hence, we conclude that this is indeed a perfect binary tree. So a first important property is that the number of leaf nodes in a perfect binary tree with k internal nodes is equal to the number of k plus 1. So, in a perfect binary tree, every internal node has exactly 2 children, and here let us denote as n the total number of nodes in the tree, k as the total number of internal nodes, and u as the total number of leaf nodes that we have in this tree. Now, to prove this property, we also need to take into consideration the number of edges. Notice here that each internal node has 2 children, so each internal node contributes 2 edges. So let us denote as m the total number of edges that we have in this tree. So we know that this is 2 multiplied by k, the total number of internal nodes. Notice how the leaves here do not contribute to any edge because the parent, as we can see here, is contributing to 2. So E is contributing to this 2, F to this 2, and so on. The leaves are not contributing. Okay, so we know also that whenever we have a tree, how many edges do we have? Well, in any tree, the total number of edges is equal to n minus 1, where n is the total number of nodes. Recall that this is a proposition that we already proved in the past. A tree with n vertices has n minus 1 edges. So now, since we know that m equals 2k and m also equals n minus 1, we can now set the two expressions equal while we also substitute the value of n, which was k plus u. And here, if we isolate u, we can see how this gives us that u is equal to k plus 1, where u is the total number of leaves, k the total number of internal nodes. And this is precisely this property, the number of leaf nodes in a perfect binary tree is equal to k plus 1, where k is the number of internal nodes. Another very important property is that when we have a perfect binary tree, the total number of nodes is 2 raised to h plus 1 minus 1, where h is the height of this perfect binary tree. This is very easy to show. Notice that in a perfect binary tree, all levels are completely filled. At depth d, there are 2 raised to d nodes, so the total number of nodes is the sum of nodes at depths 0 to h, so the sum of 2 raised to 0 plus 2 raised to 1 plus 2 raised to 2 plus, at the end, 2 raised to h. So this is a geometric series, which gives us as a result 2 raised to h plus 1 minus 1. Another immediate property is the following. All internal nodes of a perfect binary tree have a degree of 2, and this is something that is evident by definition of perfect binary tree. Okay, let us now study balanced binary trees. A balanced binary tree is a type of binary tree in which the difference in height between the left and right subtrees of any node is bounded by a small value, typically 1. Okay, let us now see an example of a balanced binary tree. Notice that here we have the root, which is vertex 1. This is an internal node that has 2 children. We have here the vertex 2. We have here the vertex 3. Notice how 3 is a leaf. 2 is an internal node that has 2 children. And 4 and 5 are both leaves. Now notice how at each node we have this metric, this df. This df is defined as the absolute value of the difference between the height of the left child and the height of the right child, meaning where children here are important for us. For example, let us analyze vertex 1. We can see how the height of the left child, that is the height of 2, is 1, as we can see, right? And the height of 3 is 0. So what is the difference? The difference is 1 minus 0. The absolute value of this difference is 1. So as we can see, that is why 1, the vertex 1, has this df value of 1. Now let us analyze 2. 2, as we can see, has 2 children. So the height of the left child is 0, the height of the right child is also 0, the difference here and the absolute value is 0, so that is why it has a df of 0. We can also see that a leaf, by definition, will have a df of 0 because it has no children, so that is why 3, 4, and 5, they all have a df of 0. So since in these three we have a difference in height between the left and the right subtrees of any node, and since this difference is bounded by a small value, which in this case is 1, this is a balanced binary tree. Here we are using the bounding value of 1. Let us now see an example of an unbalanced binary tree, again using this value 1. So if we have this binary tree, for example, this is an unbalanced binary tree. Why? Because the value of df at this particular node is greater than 1. It is 2, namely. So what is the height of the left subtree of 1, the left child? We can see here how the value of the height of this, here we can say 2, or more formally, this whole subtree has a height of the left subtree of the node 1. Here we can say the height of this node 2, although more formally what we are computing here is the height of this subtree here, where 2 is the root of this subtree. We can see how the height is 2. However, if we analyze the right subtree, right, here we can say the child 3 or the right subtree of the whole binary tree, which here has as root 1. So this right subtree, which has root 3, we can see how the height of this subtree is 0, right? It is namely a leaf in our original binary tree. So here, what is going to be the value of the df of 1? Well, it is going to be namely 2 minus 0 and the absolute value of this difference, which is 2. So we can see how this node has df equal to 2. So this is not a balanced binary tree. We can see how we have found a difference that is greater than 1. We have exceeded this bounding value. Very well, the last type of binary tree that we're going to analyze in this lecture is the degenerate binary tree, also named pathological binary tree. So by definition, a degenerate tree or pathological tree is a binary tree where each parent node has only one child. Therefore, for those who are familiar with computer science data structures, this will behave like a linked list data structure. Here we can see a very simple example of a degenerate binary tree. We can see how each parent has only one child. So it behaves like a linked list, also known as totally unbalanced in this context. What is important is to bear in mind that this type of binary trees, we can see how they are structurally equivalent to a path graph, but with some differences depending on the context. Here the idea is that in both cases the nodes are arranged in a single line, one after another. So a degenerate binary tree with n nodes has the same shape as a path graph, as the P sub n graph, but conceptually they belong to different domains, that is trees versus general graphs with different meanings attached to the nodes and edges. So essentially in a degenerate binary tree, we treat this graph as a tree, as a binary tree, and when we have a path graph, we don't treat such graph as so. A fundamental property of this type of trees is that the height of a degenerate tree with n nodes is equal to n minus 1. This is very simple to see. By definition, the height of a tree is the number of edges on the longest path from the root to a leaf, and in a tree with a straight line of nodes, that path goes through all nodes except the root, which has no incoming edges. So for n nodes we go from the root to node 1, in this case node A, then to node 2, in this case node B, and so on until the node n minus 1, which is here node E. So that is a chain of n minus 1 edges, hence the height is equal to the number of edges in this case, which is n minus 1. Finally, it is very important to know that when we are working in computer science, degenerate binary trees are usually less efficient than balanced binary trees because their operations, such as searching, inserting, and deleting, take longer as the tree grows. So this is why it is important for us to know both types of trees. Very well, and with this we end this lecture on the types of binary trees.